General Atomics Electromagnetic Systems, or GAEMS, has completed testing of guided hypersonic projectile interceptors launched from railguns. The test used a 32 megajoule railgun and the 120mm powder gun to fire identical projectiles at record hypersonic velocities to demonstrate their guided flight capabilities. The amazing atomic hypersonic Blitzer apparently shocked the world with its incredible design considerations, heat dissipation element, and more abilities. Stay tuned and keep an eye on us as we learn more about this amazing weapon. GAEMS announced that their hypersonic projectiles with an Enhanced Guidance Electronics Unit, or GEU, have been successfully tested during multiple firings from the organization's 3 megajoule or 3 MJ Blitzer TM railgun system. The enhanced GEU, which has a new battery configuration and runs GAEMS-developed guidance, navigation, and control software, has completed testing at launch accelerations of over 30,000 Gs at the United States Space and Rocket Center, Utah Army Dugway Proving Ground. So it is said that the product was designed to see if the projectile's gun-hardened guidance electronics could maintain data links and control trajectory while experiencing intense G-forces at hypersonic speeds. We have completed our contract to fabricate, deliver, and test prototype projectiles in railgun and powder gun environments, said GAEMS President Scott Forney. We demonstrated survivability and good aerodynamic performance at these velocities while testing guidance capabilities that promise greater precision and accuracy to effectively meet and defeat airborne threats. Last year, the U.S. Army Combat Capabilities Development Command Armament Center awarded the company a contract for hypersonic railgun projectile development modification. According to Forney, a guided railgun projectile integrated into the Air and Missile Defense Command Network would enable precision engagement and intercept of airborne targets. What is Railgun? A railgun is a weaponized linear motor device that uses electromagnetic force to launch high-velocity projectiles. The projectile does not normally contain explosive, relying on its high speed, mass, and kinetic energy to cause damage. The railgun employs a pair of parallel conductors or rails along which a sliding armature is accelerated by the electromagnetic effects of a current flowing down one rail into the armature and back down the other rail. It works on the same principles as a homopolar motor. The use of railguns. Railguns have been researched as weapons that use electromagnetic forces to impart extremely high kinetic energy to a projectile, rather than conventional propellants as of 2020. While explosive-powered military guns cannot easily exceed 2 km per second muzzle velocity, railguns can easily exceed 3 km per second. Railguns' range may exceed that of conventional guns for a similar projectile. A projectile's destructive force is determined by its kinetic energy and mass at the point of impact. Due to its potentially high velocity, a railgun-launched projectile's destructive force may be much greater than that of conventionally launched projectiles of the same size. The design consideration of General Atomics Hypersonic Blitzer says that the railgun's power supply must deliver large currents that can be sustained and controlled for an extended period. Therefore, the ability to deliver energy is the most important metric of power supply effectiveness. The greatest known energy used to propel a projectile from a railgun as of December 2010 was 33 megajoules. Capacitors and compensators, slowly charged from other continuous energy sources, are railguns' most common power supplies. During shooting, the rails must withstand enormous repulsive forces, pushing them apart and away from the projectile. Arcing occurs as rail/projectile clearances increase, causing rapid vaporization and extensive damage to the rail and insulator surfaces. As a result, some early research railguns could only fire one shot per service interval. In addition, the inductance and resistance of the rails, as well as the resistance of the power supply, limit the efficiency of a railgun design. Various rail shapes and railgun configurations are currently being tested, most notably by the United States, Navy or Naval Research Laboratory, the University of Texas at Austin's Institute for Advanced Technology, and BAE Systems. The lack of explosive propellants or warheads to store and handle and the low cost of projectiles compared to conventional weaponry are also benefits. However, railguns are still in the research stage after decades of development, and it remains to be seen whether they will be used as practical military weapons in the near future. Any trade-off analysis between electromagnetic or EM propulsion systems and chemical propellants for weapons applications must take into account the novelty, bulkiness, high energy demand, and complexity of the pulse power supplies required for electromagnetic launcher systems. The design of railgun. A railgun is made up of two parallel metal rails, hence the name. These rails are connected to an electric power supply at one end to form the gun's breech end. The circuit is then completed if a conductive projectile is inserted between the rails. For example, by insertion into the breech. Electrons flow from the negative terminal of the power supply up the negative rail, across the projectile, and down the positive rail back to the power supply. This current causes the railgun to behave like an electromagnet, generating a magnetic field inside the loop formed by the length of the rails up to the armature's position. The magnetic field circulates around each conductor in accordance with the right-hand rule. Because the current flows in the opposite direction along each rail, the net magnetic field between the rails is directed at right angles to the plane formed by the rails and armature's central axis. When all of this is combined with the current in the armature, a Lorentz force is produced, which accelerates the projectile along the rails, always out of the loop regardless of supply polarity and away from the power supply, toward the muzzle end of the rails. Lorentz forces are also acting on the rails, attempting to push them apart, but because the rails are firmly mounted, they cannot move. The features of railgun. If 1 ampere current flows in a pair of ideal infinitely long parallel conductors separated by 1 meter, the magnitude of the force on each meter of those conductors will be exactly 0.2 micronewtons. Furthermore, the force will be proportional to the square of the current magnitude and inversely proportional to the distance between the conductors in general. It also follows that very large currents will be required to accelerate projectiles to velocities of the order of 1,000 meters per second for railguns with projectile masses of a few kilograms and barrel lengths of a few meters. A massive power supply, providing on the order of 1 million amperes of current, will exert enormous force on the projectile, propelling it to speeds of many kilometers per second. Although these speeds are possible, the heat generated by the object's propulsion is sufficient to rapidly erode the rails. Current railguns would require frequent rail replacement under high-use conditions, or the use of a heat-resistant material that is conductive enough to produce the same effect. At this time, it's widely acknowledged that significant advances in material science and related disciplines will be required to produce high-powered railguns capable of firing more than a few shots from a single set of rails. The barrel must withstand these conditions for thousands of shots at up to several rounds per minute, without failure or significant degradation. Unfortunately, these parameters are far beyond the current state of material science. Material used. Rails and projectiles must be made of strong conductive materials. Rails must withstand the violence of an accelerating projectile, as well as heating due to the large currents and friction involved. Some incorrect research has claimed that the recoil force in railguns can be redirected or eliminated. However, careful theoretical and experimental analysis reveals that the recoil force acts on the breech closure in the same way that it does in a chemical firearm. The rails, like the projectile, repel themselves via a sideways force caused by the rails being pushed by the magnetic field. The rails must withstand this without bending and must be securely fastened. According to published material, major advances in material science are required before rails that allow railguns to fire more than a few full power shots before rail replacement is required. It is said that it has the power for heat dissipation. However, the electricity flowing through the rails, as well as the friction of the projectile leaving the device, generate massive amounts of heat in current designs. This results in 3 major issues: the melting of equipment, decreased personnel safety, and detection by enemy forces due to increased infrared signature. As previously said, the stresses involved in firing this type of device necessitate the use of an extremely heat-resistant material. Otherwise, the rails, barrel, and any attached equipment would melt or be irreparably damaged. In practice, the rails used with most railgun designs erode with each launch. Furthermore, projectiles can be subjected to some degree of ablation, which can severely limit railgun life in some cases. So what do you think about the railgun? Let us know in the comments section.